In this video, we will talk about the session 10.2, Taylor series. Taylor series are the power series we obtain from some function f(x) near some point x is a when we let the degree n of the Taylor polynomials tend to infinity. For example, we saw in the last session for the function f(x) is e to x. Near x is 0, we had e to x can be approximated by the Pnx. This is the Taylor polynomial of degree n. Pnx is 1 plus x squared over 2 factorial plus s cubed over 3 factorial plus, and the last term is s to power n over n factorial. It turns out that the larger we make n, the better Pnx is as an approximation to e to x. In fact, if we let n goes to infinity in this approximation, this Pnx will converges to e to x, and we have this e to x is the same as this series 1 plus x squared plus 2 factorial plus s to power n factorial and plus so on. Let n goes to infinity, Pnx will converge to the function e to x. The same thing happens with the Taylor polynomials for sine and cosine. So for sine and cosine, we have this 2. Sin x is x minus s cubed over 3 factorial plus s to 5 over 5 factorial minus s to 7 over 7 factorial plus, then this is negative 1 n minus 1 x to 2n minus 1 over 2n minus 1 factorial. This is sin x. Next one is cosine x. Cosine x is 1 minus x squared over 2 factorial plus s to 4 over 4 factorial minus s to 6 over 6 factorial. Negative 1 to n s to 2n over 2n factorial. So this Taylor series converge to their respective functions for every value of x. However, the Taylor series may not converge to f(x) for every value of x. If the series does converge to f(x), then we have f(x) is fa plus f prime a times s minus a plus f double prime a over 2 factorial s minus a squared plus n's power in the nth derivative over n factorial s minus a to n, then plus. So when a is 0, f(x) is f0 plus f prime 0 times x plus double prime at 0 over 2 factorial x squared, then plus n's derivative at 0 over n factorial s to power n, which is sometimes called the Maclaurin series for f. So we know the Taylor series may not converge for every value of x. Next, we look at two functions. We look at ln x. Ln x about x is 1. Ln x, its Taylor series is x minus 1 minus s minus 1 squared over 2 plus s minus 1 cubed over 3 minus s minus 1 to power 4 over 4 and plus negative 1 to n minus 1 x minus 1 to n over n and plus this is valid for x is strictly greater than 0, less than or equal to. Right endpoint is included, but left endpoint is not included. This is the Taylor series for ln x about x is 1. It only holds when x in this region. So next when we look at the Taylor series for the function f(x) is 1 plus x over p about x is 0. Here p is a constant, but not necessarily a positive integer. So the Taylor series for this function is 1 plus x to p about as 0 is 1 plus px plus p times p minus 1 over 2 factorial x squared plus p times p minus 1 p minus 2 over 3 factorial x cubed, then plus p times p minus 1 p minus n plus 1 over n factorial s to n, then plus. So this is a hold for the absolute value x less than 1. What happens at the endpoints need to be checked on individual basis. This Taylor series is also called the binomial series. So next we look at an example. Find the Taylor series about x is 0 for the function 1 over 1 plus x. So for this function 1 over 1 plus x, we can rewrite it as 1 plus x to negative 1. Then we use the binomial series with p is negative 1. So p is negative 1, we get this is 1 plus negative 1x plus negative 1 times negative 1 minus 1, so negative 2 over 2 factorial x squared, then plus negative 1 times negative 2, then negative 1 minus 2, so it's negative 3 divided by 3 factorial times x cubed, then plus so we write down one more term. So it's plus negative 1 times negative 2 times negative 3 times negative 4 over 4 factorial s to power 4. Simplify, get this is 1 minus x, then plus x squared. So this is minus s cubed. This one it's plus s to power 4, the minus. Here should be minus. And this is hold for x between -1 and 1, that is the absolute value of x less than 1.